Okay, so let's see. I'm trying to open an app and let's see if we can see on this structure. Okay, we're waiting for that, then we can proceed with natabunan ba akong screen?
Yes, ma'am. Natabunan siya.
Okay, so I can draw structure now. Oops. Okay, so you have this 3D structure here, not 3D, like a Fischer formula. Let's try to see this one. Okay, so for the first one on top, you actually see your C double bond O oxygen. You can see this one is a 3D, it's a planar one. Whenever you have a double bond in your carbon, it's always planar. Kanina sa taas, no? Sa planar, it's diagonal planar. And then you have your CH2OH. Okay, this one. And then you have your CHOH di, the second carbon, and then CH2, duha ka hydrogen and OH here. Okay, and so this is your 3D structure, and okay, so we will draw in such a way that like this one, the H and OH should be projected towards you, know. So this one is actually baliktad. No, this is the reverse, and try to reverse this structure here. Okay, so you have this structure. Gadget lang. No. Anyways, what I am trying to see, just trying to show them. I'm not asking for the band angle. Okay, so here we have already anyway, so what you have seen in here is the depiction of what should be. Oh my goodness. This one. So you have your C double bond O hydrogen and COH hydrogen, and you have your CH2OH. Okay, that's the bottom one. And you will see this, you have take a slab of this. And I take a mirror image of this other one. This one is the mirror image. Currently. Is a mirror image of the other. Okay, this one is a mirror image katong kaganina, and they cannot be superimposed, just like what you see in here. This one, okay? And so you always have to be careful when we are trying to write, because if we interchange these two, now we actually get a different orientation in space. Now, if we have OH is written to the right or OH is written to the left. If we write this way, always have to remember that it's a vertical, it's oriented away from you, and horizontal, it's oriented towards you. That is the convention of how we write on the Fischer projection as this, okay? And if you have written like this one, on the right side is your OH, no? And this one, when it's checked with an instrument, we call this one to be D, or dextrorotatory, where it rotates the plane polarized light into the positive direction. Remember your organic chemistry. And when it's called L, L means levorotatory. It rotates the plane polarized light into the negative direction. No? So they are what you call as enantiomers. And when you try to superimpose these two, they are not superposable. And you will see that these two actually are just mirror image to each other. So mirror image, we call this one to be, the structure is a mirror image of this, and they are not superimposable. We call this one to be enantiomers. So enantiomers, they have the same connectivity, but different only in orientation in space. And the only thing that they can be different for all their properties is the rotation of the plane polarized light, no? If you remember your organic chemistry. So even though learn in organic chemistry, the configuration of the chiral carbons, chiral compounds, now we have the R and S system. By convention, we write R if the priorities is clockwise, and we write S if the priorities is counterclockwise. So there is the can and gold prologue system you've learned in organic chemistry on how to designate the RNS system for chiral compounds. Okay, for carbohydrates, we designate the carbohydrates to be D and Ls. This one is proposed by Emil Fischer in 1891. So you have the D and L. D meaning it's dextrorotatory. It's written as this one based from the glyceraldehyde. No, it's a D if you have your OH here in this manner. So Fischer projection in this manner, and L if you have this projection in this manner. Okay, so there are different monosaccharides actually. No, we first start with the simplest one. So we call this one, first start with the aldoses, or in most carbohydrates, simplest one is the D-aldose. So they have the D-aldose. Okay, you have the structure here on the vertical. You always see this one. You have this Fischer projection. Now up is always your aldehyde, and down is your CH2OH. Okay, so the simplest is the D-glyceraldehyde. Okay, it's an aldotriose, meaning it's 3 carbon atom with an aldehyde. The next one is the aldotriose, no? And you have 1, 2, 3, 4 carbon atoms. So you have the CHO, C double bond OOH, and you have the CH2OH. So this one is when all the OH is written on the right side, you have your D-erythrose. It's 4 aldose. When the OH are interchanged, the third carbons, or the second carbon's OH rather, is on the left. You have the triose, okay, and then you have the aldopentose, 5 carbon aldose. So you have the CHO sa ibabaw, and then 1, 2, 3, 4, 5. The 5th carbon contains the H2OH, of course, and all the others contains the CHOH. No, so it matters now whether the COH is on the left or on the right side. It always matters. You always have to remember, because these carbons are chiral. Kaning naka-red, they are chiral, meaning any change in the orientation in space would alter whether they will be D or whether it will lead to a different sugar or different aldehydes. By the way, the common name for carbohydrates or the monosaccharides are sugars. No, they are sugars. So we're talking of there are 2 types again of the monosaccharides, the aldose, the aldehyde-containing, and the one that contains the ketone. So what we are seeing on this slide is simply those that contains only the aldehydes you have here. So you have the ribose, arabinose, xylose, L-lysose. Now you have the structure here. All sides here, one side here, interchange here. And then you have the aldohexose. You have the allose, ultrose, glucose, mannose, golose, idose, galactose, and talose. You notice that they all contain 1, 2, 3, 4, 5, 6 carbons and an aldehyde on top, and CH2OH, of course, at the bottom, and CHOH in between. The CHOH in between, change in the structure here, change in the orientation would lead to a different would lead to a different kind of sugar or monosaccharide. Okay, so you always have to remember. So you have the glucose here, all sides on the right for the OH, except for the third carbon here. Mannose is two sides in the left here. Okay, and then galactose. No? For this, we remember this kaningipang box because they may be used when we go to the disaccharide, katong two sugars, two monosaccharides for the disaccharides. Okay, so now we will just familiarize with them, and later we will just memorize katong repeating ang mga monosaccharides. So for now, we are just familiarizing what are the structures of the common or the sugars. No? So again, as I have introduced to you, this aldehyde-containing sugars, the aldehydes from 3 to 6 carbon sugars. Now you always have to recall your stereochemistry. What are the enantiomers and what are the D-aldoses? So you notice this one. You hear this one is simply what you call as enantiomers or D-aldoses. What do you think? For example, we're looking at this aldopentose here. D-ribose, arabinose, xylose, and lysose. Do you call this one as enantiomers or D-aldoses? Naka-remember pa mo? Wala na naka-remember? Okay, so I will give that as a quiz next meeting. So remember that, what are the difference in the enantiomers and the stereomers, no? So the stereomers are pairs of isomers that have opposite configurations at one or more chiral centers, but they are not mirror images. No, so there's just changes in the orientations, no, in one of the chiral centers, but they are not mirror images. So the enantiomers are this, like this one. Get the mirror image of this, and the mirror image is simply the enantiomer of this one, chiral. So this one is a chiral center, so get the mirror image of this one is the mirror image of the first. This is an enantiomer. So you have an idea what are these? Are they enantiomers? Gani for these 4 carbons, are they enantiomers or are they D-aldoses? So remember that aldoses with 3 carbons or more and ketoses with 4 carbons or more. We'll see that one later. And then the Fischer projections are in the DL systems. It's very common for sugars or carbohydrates, no? Common names for simple carbohydrates, or for carbohydrates is sugars or simple sugars. We have the common name for monosaccharides. So DL, D or L designation refers to the configuration of the highest number of asymmetric center. So D and L only refers to the series center of interest. So back to the D and L glyceraldehyde. So we always refer to the D and L glyceraldehyde. So D and L do not specify the sign of rotation of the plane polarized light, but what you have here, when you say dextrorotatory, it's because you have a positive here. This is the specific rotation here, positive. So you have here this one, that's the D glyceraldehyde here, it's dextrorotatory, and this one is liberotatory because of the negative sign. So the D and L didn't specify the sign of rotation of the plane polarized light, but we just designate that as D and L. No. So 2 sugars that differ in configuration at only 1 chiral centers, we call them as epimers. So the number of stereoisomers, remember you have the 2 to the n is the number of chiral centers. So for example, if you have 1 chiral center, there is 1 chiral center in here, This one cannot be a chiral center. This one cannot be a chiral center. So there's one chiral center. This means that there's two possible, 2 to the 1. There's two possible number of stereoisomers. If you have here 1, 2, 2 chiral centers, so 2 to the 2, there are 4 possible stereoisomers, and so on. So 1, 2, 3, 1, 2, 3. So 2 to the 3, 3 chiral centers. There's 8 possible stereoisomers for this structure. But what we have seen here, you can ask yourselves whether they are stereomers or stereoisomers. So that's my assignment to you. And next meeting we'll have a quiz on that, because this is more in a review on the organic chemistry part. So here we have the configurational relationship among the isomeric aldotetroses and aldopentoses and the aldose in general. No? So you have the glyceraldehyde again, get the number of carbons, increase the number of carbons to 4. You have the erythrous and treus. From erythrous, you get increase the number of carbon with an OH. So you have here OH, OH, you increase the OH to the right. Okay, you have your ribose from erythrous, and you have here, change this one, you have your arabinose here. Okay, so you change this OH here, you have your arabinose, so this is our reference OH, okay. And then from here, you have your OH, 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 you have the allose, and then you have your OH, OH, OH here, we change only this, you have your altrose. You copy this one, and you increase OH, you copy this, kaning 1, 2, 3, kaning tamanderia, and so you just include your OH sa ibabaw, sunod sa cho, whether the OH will be written on the right or whether it's written on the left, you get this glucose and mannose, no, from arabinose. And then from triose, okay, so you have OH, OH na, OH on the left, OH on the right, means sa obos. So we increase 1 carbon again from 4, so you get 5. So you can, your OH can be on the right or your OH can be on the left. Okay, so kaning red mo na itong reference ng OH. Okay, so from here, the structure, kani 1, 2, 3, 4, okay. Then we increase an OH, no? So kani OH, right, left, right. You have right, left, right. So you increase 1 carbon with an OH. Okay, OH can be on the right or OH can be on the left. You get this one. And then you have your lysose. You have your OH, OH, OH right. You have this. An additional OH on the right or OH on the left. You get your galactose for this, orientation, and talose for this. The D specifies, so what we've learned from the D and L, the D specifies the configuration at the stereocenter farthest from the carbonyl group. This one. So this is where the D comes from. The D based from this one, the OH farthest from the carbonyl, C double bond O. So this is where we refer our D from the D-glyceraldehyde. So when we add our carbon, number of carbons, we always start katong sa ibabaw, no, next to the carbonyl carbon or C double bond O, show here. Okay, so you notice a reference OH, CHOH is here. So you have here, kanina sa ubos, and that is where the D configuration comes from. So the D specifies the configuration at the stereocenter farthest from the carbonyl you have here. So that's why all of these are still in the D configuration. So all the configuration of the carbohydrates and the sugar and the simple sugars, monosaccharides, no, are in the D configuration. So again, I just have to mention that we have the RNS organic system, right? But in sugars and carbohydrates, we have the D and L proposed by Fischer. You have this one. So whenever you see a structure like this from the Fischer, you always have to think of the carbohydrates. And the D refers when the OH farthest away from the CHO next to the CH2OH is nadiri. Okay. Farthest from the CHO. Okay, if you have your structure here, let's say mannose, then the OH is on the right from the CHO. This is the farthest from the CHO. Now this one, the fifth one, this because this is the chiral carbon here. And this is where the D is being specified. No? So D na siya tanan. The configuration is D. So prefixes such as rib, arab, and glock specify the configuration of all the steric centers in the monosaccharide relative to one another. And when you write the suffix "-os" indicates that the compound is a carbohydrate. Okay, so you just have to remember whenever we talk about aldose, it's a monosaccharide, it's a carbohydrate with an aldehyde in it, and -os because it's a carbohydrates. So the three most abundant hexose, you have the D-glucose, galactose, and fructose. When you say hexose, 6-carbon monosaccharide hex. No? You have the glucose, galactose, and fructose. So glucose, galactose, and fructose, wala pa diri ah. Okay? So we'll see later on sa next one ni fructose. Glucose by far is the most abundant of the three and is known as dextrose because it is dextrorotatory. So what is here? Where is your glucose? You have here. And D, it's a dextrorotatory. But D doesn't mean dextrorotatory. The reason I mentioned earlier is because it's indicated, its specific rotation is already indicated. So glucose by far is the most abundant of the three, known as dextrose because it's dextrorotatory. So other names for this glucose monosaccharide includes grape sugar or blood sugar. So the human blood normally contains 65 to 110 milligrams of glucose per 100 ml of the blood. So our blood, of course, is also contained rather sugar by the sugar glucose or monosaccharide glucose. So that's why it's also named as blood sugar. So aside from being named as dextrose or grape sugar, glucose also named as blood sugar. So we mentioned earlier katong epimers are sugars that differ in configuration at only one chiral center. So here we see on the structures of the mannose, glucose, and galactose. No? All the structures here are, you have the glucose, COH, so OH, CH2. Okay, but between mannose and glucose, you notice that there is one structure that they differ, and because of that, the different carbon 2, they considered to be as epimers. For galactose, now you have all the same sequence of the OH on chiral carbon, but on carbon 4, there is a change in the HOH. So a change in only one chiral center. So you call that one to be an epimer. So glucose and galactose are epimers, and mannose and glucose are also epimers, but not mannose and galactose. Okay, so they cannot be kay daghan sila og two carbons. I think there are different by 2 carbons, but only glucose and galactose and glucose and mannose are epimers. Okay, so let's see enantiomers D versus L. So here is the structure of a fructose, no? It's one, we'll see later, this is a different kind of a monosaccharide where it doesn't contain an aldehyde, but rather it contains the acetyl band O. So what you'll see in here is that in its structure, you have the OH here. You have 1, 2, 3, 4, 5, 6 carbons. And you have the chiral centers, carbon, 3 chiral centers here. And you get on the mirror image of this, you will have H, OH, OH. So whatever on the left or right rather here becomes on the left side on the mirror image. Okay, in the same way like how we write this one, whatever on the right becomes on the left here. That's how you write on the mirror image. So this one, they are not mirror images of each other. So they are not enantiomers. When you write on the mirror image, you remember your organic chemistry, you write on the mirror image of this. So whatever on the right side of the chiral center, the Fischer projection becomes on the left side of the Fischer projection, and on the left becomes the right side. Because if you look at in the mirror, no, if kaning side, look at the mirror here, yung una makita sa mirror, kaning sa front, no, sa front. So pag tanaw mo sa mirror, ang nasa mirror is nanin siya sa left, nanin siya sa right. Okay, so here we call this, the OH here is at the right side with respect to the C-double bond OOH, no? So therefore this is a D, and this structure is what you call a fructose. So when you get on the mirror image, if the first structure would have a D structure like this one, then this mirror image will have an L configuration for sugar. So again, we use the capital D and capital L for the configuration of sugars. No, kasi itong reference sa D, kaning pinaka OH from the functional group C-double bond O, okay, the OH. Most but not all natural sugars occur in the D form. So our taste buds actually are very, very chiral. Imagine if lahi ang iyahang configuration, no? The sweetness that you will see, that you will taste in sugar, if ma-alter na siyang D to L, we would be able to taste the sweet form, the D of the sugar. Let's see, draw Fischer projections for the 4 aldehyde-containing, which are D monosaccharides, which are L monosaccharides. 4 aldehyde-containing. So what are the aldehyde-containing? You have here this one. 1, 2, 3, 4. Okay. So you have the structure, you can draw on all the stereoisomers. Sige, panguntan na, stereoisomers pa. Draw the 4 aldehyde-containing, which are D monosaccharides and which are L. Okay. So you have the structures 2, diba? There are 2 chiral centers, so 2 to the 2, there should be what we have seen in here are only 2, or only what is drawn in here only 2. But if you look at the structures of this, there are actually 2 chiral centers. So the formula 2 to the N, there are 2 chiral centers at 2 to the 2, so there should be 2 stereoisomers that will be written out of this. So what you have seen in here are only the stereoisomers, so you should write on the unless you have a question, you should be mindful of your cell phones. Okay, so again, what you have written in here are only the stereoisomers. Okay, so if there are 2 chiral centers, you should be able to write 4 na nabili mo. Okay, so let's have an example of that problem, which is just a review on what you've learned from the organic chemistry. So draw on the Fischer projection of 2 aldehyde-containing. So there's 1, 2, 3, 4 for carbons. Of course, you have your OH. Remember from your glyceraldehyde, diglyceraldehyde, the OH should be on the right. Now this is our reference. Farthest from the CHO. You see the bond O, we add carbons. So your carbon can be on the right or can be the left. Okay, so you have this erythros and kani, this one. So what we have written or drawn earlier is kani OH na to on the right. Kani. So you have CHO, OH on the right, and CH2OH, and then your additional carbon here can be on the right or can be on the left. So these two actually are what we call as diastereomers. Now we draw on the mirror image of this. Pag draw na sa mirror image, whatever written on the right here will be written on the left. And on the left here will be written on the right. So these two actually are what we call as pair of enantiomers. And here, what we have are from this structure earlier that they have already additional, the OH is on the left instead of the right. So you draw on the mirror image of this, you have the HOH on the left and the OHH on the right, and of course CHO and CH2 here. So to draw, we learned that in organic chemistry, you draw in a Fischer manner like this one. It's very difficult, or tedious rather. It's very tedious if you have to draw on the wedge and the broken line to just simply show on the orientation in space, 3D manner. So that's why we have this Fischer projection and how we draw on the chiral centers, particularly for sugars. Okay, so this is just a review, simply a review on what you've learned from organic chemistry on enantiomers and diastereomers. Okay, review on that, and we'll have a quiz next meeting. Now let's move on another kind of monosaccharide, which are the ketoses. The ketose contains a ketone containing sugar, as I mentioned earlier. So the simplest is the 3-carbon sugar. Okay, that are ketose. So the one that I have already mentioned, the dihydroxyacetone, you have for an acetone, it should be CH3, cetyl bond O, CH3. And when we replace the one hydrogen in CH3 with OH, and this one hydrogen here with OH, you have CH2OH, it's OH. This one is considered to be dihydroxyacetone. I don't know if you understand what I'm talking about. Acetone manggod kay acetone is simply kaning structure. Okay. Kaning structure kani ikaduha, no? CH3 cetyl bond OH. When we replace one hydrogen with OH, that's when you consider it to be instead of CH3, we replace it with an OH, then that's when we learned about dihydroxyacetone. Okay, so simplest one for ketose, dihydroxyacetone. Next is a 4-carbon. And then this is our reference. Our reference on the cetyl bond O. So if CH2 cetyl bond O, we add 1 carbon. We don't have a chiral center here. Okay, walay chiral center. So we don't have an enantiomer or a stereoisomer since there is no chiral center here. There is no carbon that is bonded to 4 different double bottom. So the first chiral sugar that is from the ketose is a 4 carbon sugar, or the tetrose. Tetrose, that is a ketose. In particular, we name this as erythritolose. So you have CH2, cetyl bond O, kopyahan lang na ninyo.